Hello, I'm Byung Kim. I'm going to present our paper, Context-Aware Planning and Environment-Aware Memory for Instruction Following Embodied Agents. The interactive instruction following task requires an agent to complete tasks with interactive reasoning for accurate navigation planning and for object localization for interaction. Such interactive instruction following tasks pose several challenges. First, while completing a task, the agent often plans to interact with irrelevant objects by losing the context of the task. In addition, changing object states during object interaction can potentially result in unintended interactions. To effectively address these challenges, we proposed context-aware planning and environment-aware memory. For action planning, we divide a long horizon planning process into two distinct phases, subgoal planning with context prediction and detailed action planning. To keep track of dynamic object configuration, we maintain changed object states for interaction with correct and intended objects. For action planning, context-aware planning first predicts a set of task-relevant objects as a context. After planning a sequence of subgoal frames, it incorporates the context into the subgoal frame sequence, and this results in a subgoal sequence. For each subgoal, a corresponding detailed planner predicts a sequence of detailed actions executable by the agents. We provide more details of context-aware planning step by step. First, given a natural language instruction, context predictor predicts a set of task-relevant objects, and we denote it by a context. Meanwhile, for the same instruction, subgoal frame sequence generator plans a sequence of subgoal frames. Each subgoal frame contains an action and metaclasses related to the action. The metaclasses are replaced with the context later. Once the subgoal frame sequence is planned, we incorporate the predicted context into the subgoal frame sequence, and now we have a sequence of subgoals. For each subgoal, we invoke a detailed planner corresponding to the subgoal. The invoked detailed planner plans a sequence of detailed actions executable by agents based on the subgoal. In addition to context-aware planning, we propose an environment-aware memory to keep track of dynamic object configuration. Specifically, we propose three types of memories: object relocation tracking, retrospective object recognition, and object location caching. When completing a task, the agent often faces some scenarios where the agent needs to relocate multiple objects of the same class to the same location, such as move 2 tissue boxes on the toilet. To avoid redundant interaction, we propose to maintain information about the most recent location of each relocated object in a 2D coordinate and exclude it as a future navigation target. During multiple interactions, the agent might not be able to recognize some objects with different visual appearances. To address such an issue, we retain the latest segmentation mask of objects and use them as the current object mask if the agent fails to recognize it. Finally, the agents may need to revisit some objects, such as some slices, after slicing an object. For efficient navigation and object interaction, we cache the 2D locations and the segmentation masks in memory for objects whose states change. To validate our context-aware planning and environment-aware memory, we adopt the recently introduced Alfred benchmark. The agents are required to complete long-horizon household tasks that incorporate object interaction and state changes. We observe that our approach outperforms previous state-of-the-art methods by large margins, including the main metric, test unseen success rate, including settings, the use of the templated action sequences, and step-by-step instructions. In addition, we conduct an evaluation study for our proposed context-aware planning and environment-aware memory. We observed noticeable drops from the evaluation of each and both context-aware planning and environment-aware memory. This implies the importance of each proposed component. For more details, please visit our paper and the project site. Thank you for your attention.